integrate with respect to y, because if we drew our rectangle this way, right, we would have, it would never change. We would always have this one on the right side, this one on the left side. So let me draw a little arbitrary rectangle in here right now. Like this. Right? That's a rectangle. And then what I'm going to do is exactly what I did in the other one. I'm going to create a copy of this. Now remember how I did the copy over here and I put the x-axis and I drew the rectangle? We found the... We're going to do the same thing, but this time we have to do it on the y-axis. So my copy is going to be below this. And then I'm going to draw my rectangle. My rectangle actually touches the y-axis, doesn't it? Like that? Yep. My axis of rotation is this. The blue function always touches this side, right? Yes. And which function touches the bottom? The x is 0, which I used black. I wish I would have had another color. This black one right here. Right? Do y'all see that? As I move this rectangle up and down, the blue one's always on the right, the black one is always on the left. So what am I going to have to do if I'm going to integrate with respect to y? All my curves have to be written as functions of y. And the way that they're given to me, they are this is a function of x because it's solved for y. You need to solve that for x.
So we e y?
You take e on both sides. Right? That's what you do to kill off the natural log. So what I'm going to do here is I'm going to convert, because I know I'm sideways, I'm going to convert this e to the y equals e to the natural log x, which means e to the y equals x. This is my function of y. Understand that? So this blue curve is e to the y. And then what's the black curve over here? 0, right? So let's talk about the outer radius. What's the outer radius? The distance from the axis of rotation, to the outer edge of the rectangle, which for us is just e to the y. And then what's the inner radius? 0. So you're actually standing on the edge of your rectangle is on the axis of rotation. So this inner radius, which I can't really measure, is 0, right? Understand that?
Yeah.
It's still a washer?
It's not a washer, it's a disc.
So when we do it,
It's a disc.
So where's the inner radius coming from?
It's going to not contribute at all. In the formula, it's 0, so it's going to wipe that out, right? Which kind of makes sense, right? Yep, it's the washer formula works when it's a disc because the inner radius is 0, right? So that washer formula is even better than a disc formula. Yes. I encourage you to do it just for fun, just to get used to drawing things in 3D. But I'm not going to require it. This is what I would want to see. And feel free to add as much detail to this as if you want. You know, you could say that this is R out. You could say that this is R in. You know, the more you put there, you know, the more I can give you credit, even though you may mess something up. Yes?
so with the, like, when we do the integral, it's going to be 0 to ey?
Yeah, let's see what it's going to do. Let's see what we're going to do here. The volume will be equal to pi. That you can't get wrong, okay? That's going to be pi. Well, you can get it wrong if you forget to put it. Okay, we are going to integrate from where to where? 1 to 2, and that's because this is a sideways rectangle. Our limits of integration are restrictions on y, which we didn't have to find. They're actually given to us in the problem from 1 to 2, right? That rectangle will only vary between 1 and 2. So 1 to 2. And then outer radius squared. So e to the y squared minus 0, which I'm just writing it in detail, all right? dy, not dx, right? 0 squared? Get your calculator. That's why you have that fancy thing. All right, v is equal to pi integral 1 to 2 e to the 2y dy, because e to the y squared is e to the 2y. And that's it. Whatever that number is represents the volume of that solid, and we call these solids of revolution. Revolve. But I always have to put my fist up. Revolution. It's a solid of revolution. It's a new dawn. All right. Y'all seem to be picking this up. I don't know. That's a good thing. So I'm going to continue. As you know, hopefully, by now, you only get good at these when you go try them at home. Okay, let's find the volume of this solid of revolution of the region bounded by Right, I thought about these before class, and now I'm having second thoughts. Okay, I'll just do this one. No, I'm still changing my mind up here. Hold on. Okay. Y equals e to the negative x. Y equals 1. X equals 2. About y equals 2. Oh, so that's different.
So that's going to be.
Yeah, what is that? That's our axis of rotation now. Let's start with our region. E to the negative x. Looks like e to the x, except it's reflected on the y-axis. So instead of going like this, it goes like this. I'm going to move that and put that over here. Okay. Y equals 1 is what?
It's a line.
Horizontal line, right? Y equals 1 is a horizontal line. Goes through y is 1. Doesn't e to the x hit at 1? E to the negative x hits at 1 because e to the 0 is 1. So this goes like this. This is y is 1. X is 2. Vertical line. Somewhere out here. And that's it, right? What was that, a question? I didn't hear it.
The region is really small. Right?
Yeah, it's kind of a small region. So, you know, sometimes when you draw these initially and then you see your region, you're like, wow, that's too small. So you redraw it and make it bigger, just for your own sake. Because if you have this little tiny little thing on your page, it's better to just redraw it. I think this is big enough for me to work with, though. Is that okay with you? All right, do you see the region? Okay. So we want to take this region right in here, and we want to rotate it around y equals 2. Y equals 2 is a horizontal line going through 2. Here's 1, here's 2, right? My axis of rotation is this dotted line instead of the x-axis or the y-axis, right? That's different than what we've done. But the setup is all the same. All right? Watch. I'm going to just I didn't draw my rectangle. I'm going to do a little vertical rectangle in here. All right, there's my little vertical rectangle. And I imagine taking that and wrapping that around, right? Wrapping it around, moving it left and right. So I'm going to have a bunch of washers. Over here, This is my x-axis, right? Now you may not think that matters. That's going to play into things here in a second. Up here is my axis of rotation. That was y is 2, right? And then my little rectangle is right here. Just sitting there, right? We have the top edge, okay, of this rectangle is there. And that's always going to be the red. And the bottom edge of this rectangle is always going to be the blue, isn't it? For our formula, we need an outer radius and an inner radius. Do you see why this is different than before? Yes? Because you're actually standing, your axis of rotation is here, right? So your outer radius is actually the distance from this axis to the outer edge of the rectangle, which is the blue, isn't it? And the inner radius is the distance from the axis of rotation to the red. Do y'all see that? So we got to compute those. So let's see if we can get the blue one first. What is the distance from here to here? So you know the distance from here all the way to here is 2, isn't it? And you know the distance from here to here is e to the negative x. So the distance just from here to here should be the 2. Take away the e to the negative x. Yes or no?
Yes.
Yes? Okay. So this should be 2 minus e to the negative x. Not the other way around, not e to the negative x minus 2. 2 take away, so 2 take away how much? Just that much. And that much right there is e to the negative x. How about the red one?
Just 1.
Distance from here to here? Well, it's 2, right? Take away the distance from here to here. And since this is constant, right, it's 2 minus 1. That's always going to be 1. That's it. That's your outer radius. That's your inner radius. You've got your limits of integration. Do you know where you're going to vary your x from? 0 to 2. We're there. If you have a question, please don't hesitate to ask.
You said the x-axis.
I'm not answering questions right now. No. What now?
You said the x-axis was coming to.
Yeah, so in a minute, you're going to see it. Right here, that distance from here to here is x, but it's not going to play a part in this problem. Just hang tight. Okay, so you said it's going to go from 0 to 2, right? Then outer radius, which was
All right, 2. Yeah.
2 minus e to the negative x squared minus 1 squared, which is 1. I'll just write 1 squared, and then d
Y. No, x-axis, sorry.
x. And you could expand that all out and do all that? Okay. No questions? All right. Good. We'll do another one. Let's do this same problem, okay? Exactly the same problem. I'm going to change your axis of rotation. So same exact setup. This time let's do it about y equals negative 3. Take a minute to try and draw it out. It's the same curves, different axis of rotation. While you're doing it, I'll redraw it over here too.
minus that because one is the bigger curve?
No.
No?
That's a great question. That's why it's important for us to draw the picture. When we draw the picture, we don't care where we are. We want to be looking from the axis of rotation to the edge of the rectangle. It no longer matters to us which one's on top or bottom anymore. What matters to us is which one's further away from the axis of rotation. Okay? And turns out you can still kind of do it that way, but because you're going to square it anyway, so it's not going to matter. But I'm trying to give you a method that's going to continuously work no matter what. So this is... Okay, have you had enough time to maybe draw it out? You should have something like this. Axis of rotation's down here now. Here's your little picture. This is your axis of rotation. I need an outer and an inner radius. So you must be standing as if you're looking out, standing on the axis of rotation, looking out to your rectangle, which is out there on the ground. And you're seeing the furthest edge from you, which is this one, right? This is now your outer radius, isn't it?
Yes.
How far away is that red edge? 4 units. See, I agree that this is -3, but we're looking at a distance here, aren't we? So the distance from here to that edge is 3 plus 1 because it was constant, wasn't it? 1. So that's 4. Now the inner radius is the distance from the axis of rotation to that bottom blue edge, which would be
-3 minus
3 plus
distance 3 plus how much? E to the negative x. So 3 plus e to the negative x. Do y'all see how that works? Yes.
So since we're looking for the radius, we don't care that it's we don't care for like the negative.
We don't, because it's a distance. We're looking at it as a magnitude, like how far away it is, right? If you were to be standing here and get a measuring tape and measure out to that edge, you would have to, count this as 3, not as -3. See, if you count it as negative, then what's going to happen is you're going to be telling me -3 plus 1, you're going to say it's -2. You're going to say the distance from here to here is -2. There's just no way it's -2, right? Yes?
Do you get like a deviation or a marginal of error, since like you could draw your box still within the confines of our boundaries, but the distance from E to the x varies close.
Yes, it does.
So do we have a margin of
Nope.
error?
Nope. Nope. I don't know if I'm translating what you're saying. Are you saying because as we move this over, it gets smaller?
tinier, yes. So it's still
But it's still something, right? Until I get to 1. Or sorry, until I get to 0. But at 0, they're the same function, so the difference between them is 0. But if I go anywhere to the right of it, I'm going to get some area. So that's the beauty of the Riemann sums. The limit allows you to cut it up into an infinite number of rectangles. So you're going to get every single sliver. It's amazing. I mean, it is amazing that we can do this. That's the magic of calculus, of the Riemann sum. More importantly, of the fundamental theorem of calculus, which gives us a way to get the answer without actually having to do the Riemann sum. Right? The integral gives us that answer without actually having to add up an infinite number of rectangles, which you can't do. All right. So my formula will be pi, okay, integral 0 to 2, 4 squared. So let's do it. 16 minus this one squared, right? I'm just going to put that one in parentheses. dx. And that's it. All of these things that I put up here so far are things you can integrate. You would have to expand them out, multiply this out. E to the negative x, you could integrate that. So these are all pretty well-behaved answers we're getting, yeah? Yes?
In the homework, like when we solve for it, where we have like an e to the x or something, or a natural log, and we plug in a number, do you want us just to leave it as e to that number, like natural log to that number?
Yeah, like natural log 2 or something.
Because I was trying to do the homework and I was starting to get decimals and like,
Yeah.
I don't know if you wanted us to leave it like it is.
You know, you should be comfortable with both. Like, you should be able to leave it as an exact answer and convert it to a decimal. Because if we actually wanted to know the volume, if I tell you the answer is like all this stuff with E and natural log, that really doesn't give you an idea of what the volume is. If I tell you it's 42.75, then you're like, oh, okay. That makes sense. Yes? Because we're integrating with respect to x, so we want to know what the x will vary between. And going back to this, the rectangle has to be slid left and right here, all the way through the region. And that's why we're varying x from 0 to 2. Got it? You were thinking up and down. Okay. All right. Good, good? Man, I might get out of here early today. No, I'm kidding. Oh, man. All right. Let's do this. How about the region bounded by y equals x minus 2 squared y equals, hold on a second, 4 about the y-axis. Ready to draw it?
Yeah.
Okay, so
It's just x squared moved to the right.
yeah, this is x squared, move to the right too. So 2, draw it. And I know it's going to be a parabola, but before I draw it, y equals 4 is a horizontal line, right? At 4. And I believe that this parabola hits it at 0, doesn't it?
Yes, yes.
So it's going to come up and hit here, and then it's going to hit over here. Y equals x minus 2 squared. Y equals 4. Everyone okay with the region? And you want to rotate that about what? The y-axis. So, okay. I want you to think about that just for a minute.